In this problem, we have two connected buckets. They're connected by a rope, which is runs over a pulley. The pulley is light and massless. The rope is light as well. And we're asked a series of questions. In part A, we're initially asked, if we hold on to the lighter bucket to keep it from moving, what is the tension in the rope? So here's our lighter bucket. If we hold on to the lighter bucket, the heavier bucket won't fall. So how do we find the tension? Well, to find the tension, we are first going to draw a free body diagram. And since we have two objects which are connected, we need two free body diagrams. So let's consider M1 first. For M1, we have the weight, not the weight, the tension going up and the weight going down. And we also know something about the net force. The net force has to be 0 because the mass 2 is in static equilibrium. Alright, so let's label this T1, weight 1. And now for the lighter mass, again we have a tension force upwards, and downwards we have weight, and we have the force of us holding on to the bucket. So we'll label this T2, W2, and our force by our hand. Okay, to get the tension, note that the T1, the magnitude of T1, has to equal the magnitude of T2. And we'll just call that T. This is because it's the single rope, and the tension everywhere in the rope should be the same. And let's look at bucket 1. And I'm going to apply Newton's second law to bucket number 1. Newton's second law says your net force is equal to mass times acceleration. So our forces are all in the y direction, so we can write the y components as T, the tension, minus the weight, and that's equal to mass times acceleration. Now in this case, our acceleration is 0, so we have T minus W1 is equal to 0. And we can solve for T. It's just equal to W1, which is 120 newtons. There. So that's the answer to part A. The answer to part B is actually very similar. But we'll go through it just like we did for the first case. We need a free body diagram. So let's draw that. Here is one coordinate system, and we have two objects, so we need two free body diagrams. Okay, let's label our direction Y, and let's consider our first object. So now M1 is on the ground, so we know that there's still a weight acting on our object, and there's a normal force. And in this case, we have a net force, which is again equal to 0 because we're in static equilibrium. So let's draw this as tension 1, weight 1, just like that. Alright, now, what about bucket number 2? So for bucket number 2, we have the following. We have tension, which is upwards, and we have the weight, which is downwards. And again, our net force is equal to 0. And we'll label this as weight 2, tension 2. And as before, we know that the magnitude of T1 is equal to the magnitude of T2, which we'll call T. Now let's consider bucket number 2, and we'll write Newton's second law out for it. We have the tension force, which is upwards, so we have T, and weight is downwards, so its y component is negative W2, And Newton says this is equal to mass times acceleration. That's mass 2, by the way. But we're in static equilibrium, so that's 0. So this implies that our tension force is equal to weight 2, which in this problem is 63 newtons. Okay. So that's part A and part B. Sorry, not part B, part C. What about part B? So part B, we have, we release the lighter bucket as that we were holding in part A, and the whole thing's going to fall. So we want the tension in the rope when we've let go of M2 and M1 goes falling to the ground. So we'll draw the free body diagram, as always. So we need a coordinate system. So for bucket 1, we have coordinate system. For bucket 2, we need a coordinate system. Okay. Here is our object. Y is upwards. And let's draw the forces acting on M1. M1, we have a tension force upwards. And we have a weight which is downwards. And the weight is going to be larger in magnitude than the tension force because the net force has to be downwards because the bucket number 1 is going to fall. Alright, what about bucket number 2? Again, we have tension upwards and we have weight which is downwards, but in this case the weight is smaller in magnitude than the tension. Alright, so there's our free body diagrams. Let's write down a few things. First of all, I forgot to write the net force. The net force for bucket 2 is upwards. Things to note, because it's the same rope and it's light, the magnitude of T1 is equal to magnitude of T2, which we'll call T. And also, bucket 1 and bucket 2 are both going to accelerate. And they're going to accelerate with the same magnitude, but they're in opposite directions. So A1, the acceleration of bucket 1, is going to equal the negative of A2. And we're going to call this minus A. So in this case, A2 is just equal to A. So we can get rid of some subscripts. Alright, let's write down Newton's second law for bucket 1. As before, we have the tension, which is upwards, and we have the weight, which is downwards, and this is equal to mass 1 times the acceleration of 1, which we can write as minus m1a. Okay, so that's our Newton's second law for bucket 1. For bucket 2, we have the tension force, which is upwards. We have the weight, which is downwards. And this is equal to mass 2 times acceleration 2, which we can write as m2a. Okay. So here we have two equations and two unknowns. We don't know A and we don't know T. So we can actually solve this system. Let's write out this system again. So T minus W1 is equal to minus M1A. And we have T minus W2 is equal to M2A. And there are many ways to solve this. What I'm going to do is I'm going to subtract this second equation from the first. So when I do that, notice that the T's will cancel, and I'll end up with W2 minus W1, and this is going to equal minus A M1 plus M2. So these T's cancel, and I could solve for A. A is just equal to W1 minus W2 over M1 plus M2. Okay, so now that we have A, we can actually go ahead and find T. To get T, we just have to substitute A into one of these equations. So I'm going to use the second equation here. So we have T minus W2 is equal to M2 times A, which we've just discovered is W1 minus W2 over M1 plus M2. Okay, now there's a couple of things we need to note. First of all, M1 is just W1 over the acceleration due to gravity. So that's 120 divided by 9.81, which I believe is equal to 12.2 kilograms. And you can do the same thing to get M2, and you'll find that that is 6.4 kilograms. So we can use these numbers in our equation. We know W1 and W2, so we can go ahead and solve for T first of all. T is just W2 plus M2 times W1 minus W2 over M1 plus M2. Alright, now we can just plug in all of our values for these quantities, and when I did this, I found that the tension in the string, or in the rope, should be 82.6 newtons, or something close to that, depending on how many significant figures you used in your calculations.